We're going to use the work energy theorem to estimate how much work is done to catch a Major League fastball, and then in the process of catching it, if you estimate what the displacement is, use that work to estimate the force that's exerted to catch and stop the baseball. So first part, we want to find the work done to stop a 44 meter per second, so it's about 90 mile per hour fastball. And baseballs have a regulated mass, so the mass of our baseball is 142 grams, which we want to convert to kilograms because we're using MKS. So dividing by 1,000, that's 0.142 kilograms. All right, the work energy theorem tells us that the work done is equal to the change in kinetic energy, and change in a variable is always final minus initial. So final kinetic energy minus the initial kinetic energy. And we're talking about catching the baseball, so the final kinetic energy is 0. It ends in rest in the catcher's glove. So if we can find the initial kinetic energy of our baseball, then we automatically have the work. So the initial kinetic energy, a half mass of the baseball, initial speed squared. We know all of those, so we can just substitute them in. 0.142 kilograms and 44 meters per second squared. When I do that, I get 137 joules of kinetic energy. So we've addressed the first part, the work done to stop the baseball, keeping the minus sign in place, minus 137 joules. It's perfectly fine to have the work done by a force be negative. That just means that the force that did that work is reducing the kinetic energy of an object. And clearly, when you catch a baseball, if you do it correctly, you reduce the kinetic energy of the baseball. All right. Now, what is the force to stop the baseball over a displacement of just a half centimeter, so 5 millimeters. I would not recommend this as a catcher. You're gonna try to catch something, especially something moving fast, by pulling your mitt back in the time that the ball first makes contact. And here in just a second, you're going to see exactly why. So let me draw a little diagram of what's going on with our baseball. So there's our baseball. It is undergoing a displacement while it's being caught, delta R, and it's a force acting on it to stop it in the opposite direction. Now, force is measured in newtons, displacement is measured in meters, so you can't directly compare like the displacement vector and the force vector. They're on the same diagram here, so that we can show their direction of one relative to another. But clearly I can't add 5 meters to the force exerted by the glove on the baseball. That's a nonsense statement. But we can multiply these two vectors together through the dot product, and that's what we're going to do. So the work done is equal to the force times the displacement delta r. So that's the magnitude of the force, magnitude of the displacement, times cosine of 180 degrees in this case, because the displacement points opposite the force. And cosine of 180 gives me -1. So from the previous part, the work is minus 137 joules. I have a minus sign from the cosine of 180. I have the unknown magnitude of the force that the catcher exerts on the baseball, but I know the displacement. He does it only over 1/2 centimeter, so that's 5 times 10 to the -3 meters. Very small displacement. There's 5 millimeters. Divide both sides by delta r, and I can get rid of the minus signs because there's 1 on each side. It's going to give me the force is 137 joules over 5.0 times 10 to the -3 meters, and a joule is equal to a Newton times a meter. So dividing a joule by a meter will give me the correct units of a Newton, and this is going to give me 2.75 times 10 to the 4th newtons, which is a huge force, which is why this is a really not smart way to try to catch a baseball. It'd be even worse if you leaned into it while you're catching it, but you definitely want to have less pain and pull your mitt back as you're catching it. That extends the time of the interaction, and that reduces the force.